Welcome, everyone. My name is Mark, and I'm here with Duncan and Joe of FixturFab. In today's webinar, we're going to learn what you need in a PCB test fixture, and I can't tell you how excited I am. This is the most popular bit of content we will create this year. So with that, let me go ahead and introduce Joe and Duncan, and maybe you guys can tell us a little bit about yourselves. Joe, why don't you start?
Sure. My name is Joe Selvik, and I am the co-founder of FixturFab. I work on a lot of the software design platform and along with all the OpEx and business roles that comes along with being a co-founder.
I'm Duncan Latter. I'm the other founder of FixturFab, and I've been involved with test engineering for manufacturing for the past, 6 or 7 years now. So been deep in the PCBA functional test world for quite a bit.
All right. Would you like to tell us a little bit about FixturFab now, or wait until we get into the webinar?
Yeah, at FixturFab, kind of our goal is to modernize the approach to designing PCBA functional test fixtures. So we're building out a software platform that allows you to automatically design a bed of nails fixture by uploading the circuit board design file, whether that's Altium or KiCad. And then we identify test points, guide pin locations, et cetera, to kind of help give you the mechanical files for that system, for that fixture.
That's pretty cool. So like as a PCB designer, I don't really know too much about designing a test fixture. So it sounds like you guys are taking a lot of the guesswork out of it for me.
Yeah,
automating it.
Yep, exactly. And like a lot of the, at least the mechanical portion of designing these fixtures is pretty simple, where you're just trying to find out where the test point locations are on your circuit board and put a test probe at that same location. And so that part's been pretty easy. And we're currently working on tooling to help automate like kind of the designing of test cases for your circuit board. So like every circuit board that you have, the first test you want to do is check for short circuits on any of your power rails. And so we're kind of building tools to help walk you through like, what do you need to test on your circuit board? Do you have the test points that are needed to perform those tests and various things like that?
Cool. So I sent you files earlier today for this board right here. This is our brain board for Teach Me PCB. Maybe that's something you can tell me a little bit about as we go through this.
Yeah, exactly. And towards the end of today's presentation, we're actually going to go through and kind of design a bed of nails test fixture for that circuit board.
Sweet. All right. Well, hey, I'll just sit here in the peanut gallery and offer unwanted questions and comments. And the floor is yours. Let's get going.
Awesome. So today we're going to talk about PCBA functional test fixtures and kind of go over like why they're important, why you actually want to design them if you're manufacturing a product, as well as kind of cover like how to develop a test specification and select instrumentation and all that fun stuff. Let's kind of start at a pretty high level where let's just take a look at the general manufacturing process for a circuit board. This is kind of like put into 3 different steps, I guess 4, which I'm missing one. So the first thing that happens is your circuit board is fabricated. So the physical PCB itself is etched and solder masks applied, all those steps. After that, like the physical board exists and you just need to assemble all the components onto that. So for that, it'll go through like a solder paste machine. A pick and place machine will then place all your components on it, and it will then go through a reflow oven to solder everything to the board. After that is kind of when it enters the inspection and testing phase. There's a couple of automated systems, being automated optical inspection. This is run on almost every single board during mass manufacturing. And then there's also automated X-ray inspection where they'll actually take X-rays of the board to double check solder joints on like BGA components or something where there's a hidden solder pad underneath it.
That is certainly my favorite part of every assembly line, X-ray inspection.
It's really cool. And also like the AOI machines, like always flashing like different colored lights and like using all of this kind of computer vision to try and identify if like resistors tombstoned or in the wrong orientation. It's pretty amazing what just those two inspection steps can catch. And then kind of following the inspection steps is actual electrical testing of the circuit board. And so these are kind of like broken out into two different phases. The first being in-circuit testing, which is with the board in a powered down state. So you're not applying any power to it, and you're just checking kind of resistance and capacitance between various test points on that board. This can be performed using a flying probe machine. That's pretty common on like lower run boards or your initial prototype runs. And then if you're hitting mass manufacturing, you'll actually get a physical test fixture made, a bed of nails fixture that will perform that same test much faster than a flying probe machine where you have a series of probes having to physically move around. And then after in-circuit testing, there's functional testing, which typically occurs when the board is powered up. So this will be the first time you actually apply power to it, and that can cause, kind of components that are, shorted or wrong orientation to actually blow up, and that's why you want to have it happen after your in-circuit testing phase. And during functional testing, you'll typically check like voltage rails, make sure all your power circuitry is correct, program any processors that are on the board, and then kind of test the functional blocks of that circuit board. If there's sensors on it, you'll want to make sure those work, like if there's accelerometer or temperature sensor, as well as like if it had like a stepper motor driver, you'd want to make sure that you can actually drive a dummy load of some sort to make sure that the board's fully functioning.
Very cool.
Yeah. And so here's kind of another little look into like, what does a functional test actually do? And the main goal is to just check all the functionality of the board. So in this case, this is a SparkFun Red board, so just Arduino clone. And it has a couple of different things we'd want to test on it during manufacturing. First thing is like, are the voltage rails in spec? This has a little voltage regulator, so it takes 5 volts in over USB or a barrel plug, and then it converts that down to 3.3 volts. So we'll want to make sure that both the 5-volt line is there as well as the 3.3 volt rail. Does the processor run? So like, can we program the processor? Can we run a sample program on it or a test program? And then there's also this USB to serial communication chip. So we'll want to make sure that we can actually talk to the processor using a computer over a USB port, and then it would connect to the UART on the Arduino. And the main reason we want to do this testing is so that we can identify issues with the board earlier on in the manufacturing stage. I always like using a cell phone as an example because cell phones are completely glued together these days, and it's really difficult to disassemble them. So if you wait to test that your circuit board actually works until the phone's fully assembled, it's really expensive and time consuming to completely unassemble that and then try and figure out what's wrong with that circuit board. Whereas if you test the circuit board right after it's been assembled, you can identify all those failures like much earlier in the process.
I absolutely hear you. And taking these things apart to try to repair them or look at them or inspect them after the fact is ridiculous. In fact, the tool that I typically use, you can see just over my shoulder, right there. It's a 3-pound sledgehammer.
Just breaking it apart.
Yeah.
Get to the circuit board. Yeah. So to kind of do this testing, you kind of touch a bunch of different areas of engineering. And this is what actually got me interested in kind of functional test engineering in the first place, is you have a bunch of mechanical engineering that goes into designing a robust, repeatable jig that can mate with a circuit board over, hundreds of thousands, if not millions of cycles during mass manufacturing. To do all the kind of measurements and interface everything, there's a decent amount of electrical engineering involved, kind of selecting the instruments that will be used to program or take measurements from the device that's being tested. And then to kind of tie it all together, there's a lot of software engineering involved because you need to develop a automated test plan that will run these tests kind of reliably throughout the like manufacturing day. The kind of standard approach for this is like these test fixtures have been around since the 70s. Like it's been around for a long time. But kind of the typical way to go about this right now is to manually wire your instrumentation to the bed of nails fixture. You can kind of see this on the left-hand side, just wires everywhere. You then also have a large instrument with a bunch of expensive equipment in it, like a National Instruments PXI chassis. And then the most common software approach today is to use LabVIEW and test stand from National Instruments to kind of create your automated test plan. At FixturFab, we've kind of taken a different approach where we're kind of using what we like have termed kind of micro functional tests, with our partner Acroname, where we use in-game test fixture bases with a custom test point carrier board. And this custom circuit board goes from, or will interface the test probes for the device that you're testing and connect them directly to the instrumentation that's being used to take measurements. In this middle picture, you can see a test point carrier board on the bottom. And then these kind of cards that go into PCIe connectors are Acroname manufacturing test modules. So there's a variety of different modules for kind of measuring or controlling digital I/O. This orange one is a analog or card, so it has a bunch of high precision analog inputs and outputs. And then this back one is digital communication, so it has like UARTs, I2C buses, etc. And then for our software, instead of using LabVIEW and test stand, we've chosen to go with Python. We love Python because it's free. We've built a plugin for PyTest, and this allows us to kind of leverage all of the different modules and plugins that have been developed for the PyTest environment with our functional tests. So it's made it much, much faster to develop these automated test plans compared to us using LabVIEW. So how do we physically interface between the circuit board we're testing and the instrumentation? For this, you'll design test points onto your circuit board. So here's a picture of that same red board from earlier and a couple of the test points. To make contact with these test points, you'll use a pogo pen and a receptacle. So the pogo pen has a spring-loaded tip on it, and that will make contact with the test point. With these pogo pens, there's tens of thousands of different options for you to choose, depending on like what kind of test point you're probing, how much current's going through, how big of spring you need. And it can be pretty like mind blowing and overwhelming to try and figure out which one you want to use. So there's a lot of information on how to choose the right ones. And kind of our recommendation is if you check out engin.com, they're like our favorite probe supplier. And they have a great article on how to choose exactly what pogo pen you want to use depending on your test point.
How do you spell Engin?
INGUN.
Okay.
Yeah, they're a German-based kind of test probe and fixture manufacturer. So this fixture on the left-hand side is actually one of their fixture bases as well.
Cool.
And then for the actual bed of nails assembly, again, we use Engin test fixture bases for our production style test systems. And these consist of a large mechanical test fixture base. So this is huge or fairly large and extremely robust, like can be used for, millions of cycles. And then a piece that's actually customized for the device that's being tested is this interface cartridge over on the right-hand side. So this cartridge consists of a couple different plates that will be modified to kind of hold the device that's being tested. The green plate is called the probe plate, and that's where the test probes will actually be mounted to. The moving plate will kind of hold the dud to make sure it's flat and doesn't bend when it's pushed down inside of the fixture. And then this pressure plate will have kind of pressure fingers on it, which will push down on the circuit board and apply even pressure against it and hold it against the test probes when the test fixture is closed.
That is so much better than the first test fixture I ever built.
What did you build?
Well, it just so happens I have it right here. So this is to carry a little module, a little RF module that needed testing. So those are pogo pins right there. I can probably come up with something better to poke them with. But they're replaceable and removable. So I did that part right. You can kind of make out that they move around, and I'm not coordinated enough to make them go down. There we go. And then this is a mounting plate for a little cam clamp.
Yep.
And then the holders, the pogo pin holders went over to the wiring pad and then over here. I actually made 2 of these, and the first one worked, so I didn't need the second one. So yeah, I mean, that's Hackaday quality right there. I'm telling you. That is not production.
It's a very relevant example though, like from all of the various customers and prospective leads we'll talk to, like it's very common to see like home bro like solutions like that. And a lot of times it works, but like what happens when you do it repeatedly, or you don't have like those like weeks of design time to build something like that?
Yeah. I mean, I think I did, 20 of those little things, programmed them before I put them on boards, but you're right. Yeah. That's not taking 1,000 run by any means.
As far as we've seen, no one's like sat down, tried like standardizing the approach to like building these test fixtures, even though every circuit board typically traditionally needs one.
What about, there's nothing in IPC for test?
There's definitely a lot of stuff in the IPC standards as like for tests, but none of it really gets into like, oh, this is how you build a bed of nails tester that I found. And if there is, and I don't know about it, I'd love for people to share that.
Well, I do have an IPC contact or two. I could also reach out and see. We know Patrick Crawford, so maybe we can ask him after the webinar.
Yeah, that'd be great. Typically, it's like as soon as I'm like, I wonder how I'm supposed to do this, and then I go search, and someone has some sort of kind of article on how to do it.
Yeah,
so
and
that'd be
just
really
because there's a standard doesn't necessarily mean people are following it.
Yeah, that's very true. Kind of one of the things with manufacturing files that we've seen from kind of like Altium and Mentor Graphics is ODB++ and then IPC 2581. They're both kind of like manufacturing file formats. And they both contain a lot more information in regards to like how to test a circuit board and manufacture it. And so like those are the files that we want to start supporting on our platform, because it will give us, all the test point locations and like what the voltages are supposed to be at various locations, stuff like that. Whereas, with Gerber's, it's just a vector file for the most part. Like it's fairly dumb. You don't know what net is what. So like going to those newer file formats is going to be really interesting. And I guess like one more thing, like going on your kind of what it looked like a laser cut test fixture for the most part.
Yeah. I made that one Friday afternoon, just with the tools I had available, and I had a Epilog laser available. So that's the basis of the design.
Yeah, that's very like similar to how like kind of we started our design platform a little while ago. It's like I was like, oh, I have a 3D printer and a laser cutter. Let's see if I can whack together a Python script to automate the output. And ours was the same way. Like had a little cam, like a toggle clamp that you would screw onto it, and it just hold a circuit board down against them. And those like quick little fixtures are great for development, especially like when you're first working on a project or bringing up a circuit board. We used them a lot at a company I used to work at, like where all the circuit boards were really small and there wasn't space to put a programming header or a tag connect set of pads. And so to do the programming and firmware development, we would just make these little development fixtures is what we'd call them, put the little board in, slap it in. And then as you're doing the firmware development, you can just program it straight from your computer in the fixture instead of having to like bodge wires all over the place to try and connect to the programming pins. So they're cool little things.
Definitely.
One of the other things we like to do with our kind of production fixtures is we like to build kind of like self-contained units. So with these larger test fixture bases, we'll actually integrate all of the test equipment inside of it. So this will typically consist of like a computer. We love using Intel NUCs just because they're reliable and we've had great luck with them. Any of the power supplies that are needed to power the device under test, or the various instrumentation, and a USB hub as well. And the cool thing about this is you can show up to the manufacturer, you just have a big box that you put on the workbench, and then you just hook up a couple of things over USB and an HDMI cord to the monitor. You have a functioning test system. You don't have to wheel around a like equipment rack and deal with hooking up all that stuff.
That does raise a question in me. So you give this to the manufacturer, and I assume they get a series of, go, no-go reports. What do you do with the no-goes? What do you do if there's a problem? How do they go about figuring out how to fix it?
Yeah, so this is typically part of the test specification development, where kind of you generate a series of test cases, and the idea with each of those test cases is you're testing some part on that circuit board. So say like there's a 5-volt voltage regulator that you're testing. So you read a voltage from the 5-volt line. You want to make sure it's 5 volts plus or minus 1% or something like that. And then if you have a device fail that, you're like, okay, we don't have 5 volts on that voltage regulator. So we can't really point to exactly what component is wrong, but part of the kind of debug guide that will go along with that system is like, okay, like test case 1.2 failed. That tests the 5-volt regulator circuit. So go look at U2, which is the 5-volt regulator IC or something like that. And then what will happen is the manufacturer, like the test operator, will put that board aside with a note on it saying like, hey, this failed for test case 1.2. And they'll then bring it over to a rework and debug area where they'll try and debug what failure occurred on the board and then manually fix it.
Now, there are times I can imagine where I might want to take control of a certain net on the board. Would I do that with just some logic gates built into the circuit, like some AND gates or something? How do you go about doing that? Like if you're testing a whatever, and let's say you want to intercept a clock signal, you don't want to send it to the microcontroller. You want to, series step through that on your own with the test specification. Is that something you guys help with, or is that up to the engineer to figure out?
Yeah, this is like one of those things where specifically, like if you're looking to like inject signals, like while a IC is also running or something like that, it can get complicated quickly. So we definitely need to work closely with the kind of electrical engineer who's designing the board, as well as the kind of firmware engineer who's writing the firmware for it. And there's a couple of different ways we go about doing these things. One is like if you can like hold a processor and reset or something like that, where it will throw the pins into a high impedance state, then you can do that and kind of overload or override it using your own instrumentation. Another thing that we do quite often is have a test specific piece of firmware written, whether this is integrated within the actual production code or if it's a special image that we flash on before. But that'll give us the ability to kind of send commands directly to the microcontroller and then control various IO. The other way to do this is using boundary scan, which is another technology where you can use a programmer and actually kind of manually check what nets are connected to each other from between various kind of ICs that support boundary scan.
The reset would have been a much better example than the clock one, but I was going off the cuff. I was playing fast and loose with the rules, man. So, okay.
Clock stuff, hard to mess with.
Yeah, I was like, why did I pick that as soon as it came out of my mouth?
Yeah, I mean, it's hard enough to just measure a clock signal. Like, I mean, our go-to way to do that is have it get output via IO pin that's not being used on a processor. It's way easier to measure that than trying to probe a clock signal on an actual circuit board.
Yeah, I mean, you could have publicly shamed me on that one. It would have been okay.
Yeah. Um, so here's kind of a little bit of a closer look at the actual interface cartridge, or the bottom part of the interface cartridge at least. So there's this big green plate, which is the Pro plate. These two plates, both the Pro plate and the moving plate, are made out of FR4 or G10. So it's a fiberglass composite, very similar to kind of the substrate that a circuit board's made out of. And it's used because it's dimensionally stable and it's very stiff. So it's a great material to put a bunch of probes in that is going to have a bunch of force applied to it. The pogo pins are inserted into receptacles, which the receptacles are press fit into the probe plate. And then on the bottom side is where our custom test point carrier board is. And so this is a custom circuit board where it'll solder to the receptacles and then route those to the instrumentation for that device. So on this interface cartridge, there's just a single card that does a bunch of digital I/O checking. And then to locate the DUT on the cartridge, this one uses dowel pins, but we also use kind of spring-loaded guide pins, which kind of have like a spear tip. We really like the spear tipped spring pins because you can use them with varying hole diameters. So you don't need to make sure that you have a tooling hole of a specific diameter on that circuit board. Yep.
Hey, so if I do a tooling hole, I'm assuming you guys have like around 3mm dowel pins, somewhere in that range.
Yep. So like our go-to is like 3mm or 1/8 inch. So like a M3 hole, the clearance hole is what, 3.2 millimeters, I think, in diameter. And then like we have varying sizes, like 1/8 inch, 2mm, 2.5mm, 3mm. And we'll just choose whatever is closest to what you have. But we definitely do prefer to use the spring tip ones if it's a diameter that doesn't fit a normal size dowel pin.
And do you prefer that those are plated or non-plated through holes?
Non-plated is better, but plated is fine.
And you said an overage of about 0.2 millimeters?
Yeah, I believe that's what the standard is for an M3 clearance screw is 3.2 millimeters. It changes depending on the diameter of the hole though.
Okay, all right.
Yeah, like there are cases where, we'll machine down a dowel pin to fit a custom hole or something like that. But typically we try and just use standard off the shelf parts. Here's kind of a closer look at the bed of nails. So on the left, you can see the cartridge inside of the actual fixture. And then we have all the probes inside of the, like just underneath the moving plate. So when the fixture is in the open state, the moving plate moves up and makes sure that none of the probe tips make any contact with the circuit board. And this is to both protect the probes when the operator is like loading and unloading the circuit board, as well as prevent them from making contact with the circuit board prior to you wanting the test to actually start. One of the kind of gotchas that people run into all the time when they first start building test systems is they won't switch off power to the board. And so sometimes, depending on what pin makes contact at first, you can actually dump a lot of power through like an IC or something like that, which can cause parts to blow up. And it's all just because you didn't turn power off and on at the right time.
Whoops.
So, yep. Expensive mistakes.
So how do you deal with that?
Yeah, so a couple ways. One, use a programmable power supplies where you can like control when power is applied via software. And so you can have a switch detect when the fixture is actually closed. So in the case of this fixture, we have a inductive sensor in there, which detects when the entire frame is closed. And on other fixtures, we'll use a physical micro switch or something like that. And then you can use that to then tell the programmable power supply to like turn on power or turn off power. You can also just use like a relay. So you could have a USB controlled relay to turn power on and off. But you want to make sure you have a way of physically disconnecting power from whatever fixture that you're designing.
Got it. That's something I'm sure I would have forgotten to do at some point. So thanks for bringing that up.
It's yep. Every once in a while, I catch myself too, and like having to like go through and be like, oh, I guess you're throwing a USB relay in this thing. So it's an important one.
Yeah.
Yeah, and then on the right hand side, you can see the test probes, and these are press fit inside of receptacles. So on this board, it was very simple, but just a bunch of continuity testing between various I/O pins.
How do you do that? Just a bunch of muxes, or I mean, how do you?
Yep, that's
Oh, okay.
so that's this is the test point carrier board for that same cartridge, and so on this one we have a lot of digital I/O on this original card, and then we just have a whole bunch of muxes, and so we would just go mux through and like turn one pin on, check to see if it goes high, checks to see if it turns off. Another way to do this is to measure the resistance between two different test points, and that's probably a better way to go about it. But we did not do that on this approach. Kind of to do the resistance measurement, you can get a DMM with a multiplexer that's built into it, and so you can just hook that directly up. Or with the acronym cards, you kind of use a voltage divider setup where you use tri-state inputs to set one test point high, pull one test point low, and then you can measure the voltage between a couple resistors to figure out whether they're connected or not. Yeah, but
Cool.
yeah, checking, if a digital pin is connected or like set high and low works, but measuring resistance is definitely the best way. And then kind of the last plate for the test fixture is this pressure plate. And so this holds a whole bunch of pressure pins that will physically push down on the circuit board and pushes it against the test probes inside of the fixture. Yeah, it's a pretty simple one.
Yeah, those pogo pins, they've got forces in the range of what, like 1 to 5 newtons, somewhere in there?
Yeah, so you can get ones that are like half a Newton, but we typically use 1 to 1.5 Newton probes, and you can get stronger ones as well. And so like, by themselves, it's not that much force, but if you have, 600 or 1,000 test points on your circuit board, it adds up quickly.
Yeah, that would be insane. So 600 newtons, 60 kilograms, that's like the weight of half of me on your board.
Mm-hmm. Yeah, and it's why it's really important that you actually do some mechanical like design and engineering to make sure that board's going to still sit flat, because you have all of these point loads all over that board. And so if it's not properly supported, you can end up like bending the board and popping components off. And so that's kind of like one of the reasons why Ingen uses this big kind of black fiberglass plate, so that we can push down all over the boards on the top side against that flat piece of plastic or of fiberglass. And then kind of in summary, like our approach to test fixture systems or turnkey test systems is to use Ingen test fixture bases and cartridges. These come in a variety of sizes depending on the size of the device that's being tested. We love to use acronym manufacturing test modules inside of them. If acronym doesn't have a device that will work for the system that we're working with, we'll buy instrumentation from like Keysight or Eigel and integrate that into a rack. And then on the software side, we use our own test runner, which is built using Python. So we have a graphical user interface that's built using Qt, and then we use PyTest to build all of our test plans. We'll go through a little demo now where we'll kind of walk through our automated design service. And so this is where you can actually upload kind of the test point lists and Gerbers of your circuit board, and then design a physical bed of nails test fixture.
I recognize that.
Yeah, it's your board. So let's see here. Yeah, so if you go to FixturFab.com, there's a design button that will bring you to kind of the project creation page. And let's make a little development fixture for that Teach Me PCB macro board.
Cool.
So we'll just do macro keypad. You then need to kind of select your test fixture type. We currently have 4 different ones. Nice little 3D printed test fixture, which is very similar to your little laser cut thing. A couple of different InGen test fixture bases, and then the Dev 260, which is a laser cut development fixture. So kind of
how do I know which one to choose?
Kind of, it depends on what you're looking for. If you're looking for a kind of production style test system, like, you know, something to be deployed in manufacturing, we would recommend the InGen MA260 or MA2111. And we have sizing information on our website for the maximum DUT size. But if you're looking for something for kind of like a first rev of a board or something like that, we recommend the Dev 260. We have this Dev 101, a 3D printed one. It's something that we've been playing around with. It's kind of what we originally started with, but the Dev 260 is a much better platform, in our opinion. After that, you want to choose your receptacle type. With these, or with your test probe receptacles, there's a couple different ways that you can connect to them on the backside. There's a crimp connection, a open connection type where it's just a hole, solder cup, so you can easily solder a wire to it. There's wired ones where it comes with a certain length of pre-attached wire, and then wire wrap ones where it kind of looks like a square post for a like 0.1 inch header or something like that. So we'll just choose solder cup. For our test point carrier boards, we'll always use solder cup receptacles, just since we're soldering them to the test board. And then for the test probe tip styles, we like to use either spheres or stars. But if you're kind of probing a bunch of through hole parts, you can then choose the concave tip type. And these just populate kind of the defaults for the project. You can change these later on during the design process. So we'll do those, hit save, and it'll now bring us to the page where we can configure our device under test. And so this is where you'll actually upload the files for the device that you're manufacturing. So we'll call this macro pad or macro keypad v1 file, a test point file. So this contains the kind of test point locations and guide pin information. And then we'll also upload all of the Gerbers for this file. And what we use the Gerbers for is it allows us to kind of generate a 2D render of the circuit board that you can then use to kind of double check locations of test points and guide pins and pressure pins. So after this, the first page you get is the test point configuration. So here we can see that we have our receptacles with solder cups. That's what the -3S means. And LM2 is a sphere tip probe. And if we scroll down, we can see an actual 2D render of the Gerbers for the device. And so if you kind of hover around, you can see the different test point information. So the smaller points in red are test points. The larger ones in red are the pressure pins. And then we'll be using dowel pins to locate this board within the fixture.
How cool. So I can do that all on my own. I don't even need to talk to a human.
Yep. This is still very much kind of like early stages, so there are bugs. And if you encounter any, like, definitely reach out to us. We're quickly iterating on making it better.
Oh, I can find bugs, let me tell you.
Yeah, and it's not like super straightforward yet. It's mostly a tool we use internally, but we want to allow people to use it themselves as well. And our goal is to make it completely self-serviceable. So if you don't want to talk to us, you don't have to. But we love talking with people. So
I like talking to you too. You guys are nice, especially Joe, man. He really can just talk your ear off.
Some days, yes. I'm the one who'll answer the support email when you find those bugs.
Yeah.
Now, let me ask you, are you guys very professional about things, or do you reply back, you know, various things like, oh, you found a bug, huh? Yeah, sucks to be you.
I always appreciate it when people take their time to communicate that, like, they're using my tool, that they wanted to work again. So I do appreciate that I am friendly towards that.
That's good. What kind of information helps you to recreate or solve a problem? You know, what do you wish every user would do when they submitted a bug report?
Honestly, just copying that URL at the top because that has all the information for all the models that the various bug will be related to.
Okay.
Yep. So just this slug all the way up at the top, because that'll just help us figure out where the problem occurred. Yeah, so kind of after you configure your test points and pressure pins, you can then view a 3D render of the circuit or of the test fixture. This will take a little bit to render, usually about 30 seconds or so. And once it shows up, you can then make some adjustments to it, like where you want the DUT to actually be inside of the fixture.
And I've heard Duncan say it a few times. DUT stands for device under test for anybody out there who might be wondering what that word is.
Yep. Device under test. I'm all about my 3-letter acronyms, so I don't catch myself all the time.
It's a very common one in this space. DUT is said all the dang time. But if you're new to this space, you might not know it. So it's the only reason I brought it up.
Yep. And what I can see right here is I forgot to select the correct pressure pin. So we'll go back and fix that real quick.
Hey, Joe, we found a bug.
It's Duncan. It actually works as intended. So what you see right here in these receptacle and pressure pin drop-down menus is what kind of part would you like to populate there?
And so we'll just save that, and then let's go generate a new render. And now the pressure pin should be longer so that they'll actually be the correct height within here. And the one bug is we shouldn't let you choose the wrong ones for this fixture size.
Yeah, so this is available right now for a lot of demo-like purposes because it's honestly kind of fun. You learn a lot designing your own physical fixture. But internally at FixturFab, we have a request for a quote form because we know how to work around this right away as we still build up our resources to really get this to a user-facing platform that they can use self-sufficiently.
Yep. So there's kind of a initial render. It looks fairly centered, but we need to push it back a little bit due to these test points down here. And so we'll just kind of adjust that really quick. Do 4-centimeter offset and update the render. And kind of after you have the 3D render configured, like with the DUT where you want it to be, you can then click the bottom button, which will take you to kind of a summarized view of what's in that test fixture. And then you can also purchase it from that link. Yeah, so this looks much better. All of the test points are now actually inside of the fixture base. So we'll hit view BOM and purchasing details. And so this is where it'll actually kind of create a bill of materials for what's inside of the fixture, create a kind of estimate for how much it'll cost to build and assemble. And you can then purchase it from this point. Kind of, if you get a development fixture from us, we will machine and fabricate it, and we can typically ship these out in 3 to 5 business days. Whereas the production fixtures typically take us like 4 to 8 weeks, depending on exactly what parts need to go into them. That's mostly because we have all this stuff in house, whereas the production stuff, we have to order that.
So yeah, I think something that's worth pointing out is FixturFab is, I mean, you guys have created this from the ground up. This is your baby, right? Yeah. But that being said, it's still relatively new, so you can't have a $10,000 piece of test equipment sitting on a shelf, hoping that one day somebody comes and uses it.
Yep,
you know,
those are the basics of cash flow.
So that is something that you want to get into your design. But you know, if you're doing a design, 4 weeks isn't that bad. By the time you get your boards and your parts and everything, you should know what test equipment you need before you even start the layout. You know, at the schematic stage, you can start talking to Duncan and Joe and get it on order then. So then it's ready by the time your boards are coming off the line.
Yeah, exactly. And it's definitely better to kind of talk to us or another test system provider like as early as possible, because we can like help provide input into kind of the design of your circuit board as well. There's a lot of things you can do to make it much easier and cheaper to test, such as using like larger test point spacings, making sure all your test points are on a single side of the circuit board, and just little things like that, which will make it much, much easier to make a fixture at the end of the day. Plus, like if we know that you're going to want to test fixture in 6 weeks, we can order parts earlier so that like when it comes time and you've locked down your board design, we have parts on hand and can actually go ahead and machine them versus, starting that 6 or 8 week kind of clock when you're 2 weeks out from having product in hand.
Definitely makes sense. So it just kind of depends on what's required as to the turnaround time, because you said you can do some of these in 3 to 5 days.
Yep. Yeah. So these are development fixtures, as we call them, like the Dev 260 and so that's the laser cut one, and then the 3D printed one. We can turn those around in 3 to 5 days.
Okay.
Yep.
Very cool.
Let's see, what do I have after that? Yeah, so I have a little bit of more information on kind of like how to dive into creating an actual PCBA functional test specification, if that's interesting.
I'm interested. I don't know. What are you interested, Joe?
I think so.
All right, Duncan. We don't know what you're selling, but we're ready to buy it.
Yeah. So this is just like a pretty high level view of what we want to look at when we create a functional test system. And I believe we're using the macro pad as the example, the Teach Me PCB macro pad. So kind of the high level points when you're like looking or approaching the creation of a functional test system is the first thing you got to do is create a test spec. We typically do this like once a schematic for a circuit board has been created, but this could start even earlier in the design phase of the kind of like end product. So it's like as soon as you know, like, hey, we need a circuit board that does X, Y, and Z, you can use those requirements to kind of create a test spec from it. Once you have a test specification, you want to identify all the nets that will require test points for it. Back in the day, like, and I mean, with ICT, like if you're doing in-circuit testing, ICT testing, you want to try and put test points on every single net. Today, that's getting pretty difficult. Boards keep getting smaller and smaller. They keep getting more dense with more components on them. And so you typically can't add test points to every single net on that board. So at a bare minimum, you want to make sure that you put test points on the nets that you need to test. So this would be like your voltage rails, making sure you break out the programming pins and headers, and various test points for that. After that, we'll typically create a block diagram and identify the various instrumentation that's needed to perform the test. And so this will be like, oh, we need to measure a voltage, so we need a ADC or multimeter to do that, or like we need to program a device using SWD, so we'll put a J-link in there, etc. After that, you can then get into kind of the more detailed design phases where you'll mechanically design the bed and nails fixture. You'll do the electrical system design, whether this is just creating the kind of wiring diagram for it if you're manually wiring everything up, or the custom test point carrier board like we do. And then after that, you actually go into the fabrication and assembly stage, and then you can start the test software development. Depending on the number of resources you have, it is possible to start the test software development prior to having physical hardware in hand. But you should make sure that you like abstract the hardware stuff away, or else you'll just end up running around in circles, trying to write software when you don't actually have anything to run it on. Here's kind of a sample test spec. We just create a simple spreadsheet where we'll kind of have a name of the test case, a short description of what we're expecting to do during it, and then whatever our expected outputs are. And so for the macro pad or macro keyboard, these are the kind of test cases that we came up with. So the board has 2 different voltage rails, so we want to make sure that we do short circuit tests on both of those. After that, we'll check that both those voltage rails are actually performing at their expected voltages. And then after that, we will flash firmware onto the microcontroller. We'll typically immediately want to verify that the correct version of firmware has been programmed on there. This is just kind of a double check, okay, are we writing the right file? And then are we getting the right version from that file back? It's pretty easy to accidentally swap a file and not update the other parameters. So doing this helps you make sure you're actually shipping the right version of firmware. Also, just a side note, make sure you always have a mechanism to update your processor's firmware in the field. I don't know the number of times I've heard people being like, oh, we don't need to update that. And then, at the end of the day, it's like, uh-oh, like, how do we actually get around this? Always have a bootloader or some way to update firmware. After programming, we then get into kind of the actual functional tests on this circuit board, where there's encoder and RGB LEDs. So we'll want to make sure that works. And then we'll want to make sure that the 6 keyboard or key switches on the macro pad work.
Yeah, that version check, man, I've gotten bitten by that. Not with my own designs, but with designs I've worked on for other people. And, I'm running into bugs or whatever, and they can't figure it out, and I can't figure it out. And then we finally compare versions, and, I'm using some previous version that they've since moved on from. Google did that to me once even. It was a pain in the butt. They're like, yeah, oh, we didn't even know that one got into the field. We just had that, that was one of the very early ones. Where'd you get that?
Exactly. And like,
you shipped it to me.
Yeah. And I mean, especially like with tests, like if you have a test specific set of firmware features or something like that, someone will throw a new version of firmware that'll get programmed onto it. And then all of a sudden certain tests will start failing sporadically or something like that. And it's almost always down to like, something weird changed and it's causing some unexpected behavior on the microcontroller. And like just making sure that like the firmware that you developed the test with is the same one that's being run in production is very important. So yeah, always do it. It doesn't take any time and it'll help you.
Good advice.
Yep. So here's kind of like the test point list for the circuit board. So we just kind of take note of the designator name as well as the net and their locations. Here's a little block diagram for the test system for the macro pad. So for this one, pretty simple little fixture base. In this case, we'd use the development fixture that we just designed on our platform. To interface with the device under test, we would design a custom test point carrier board. And within this, we'd have a acronym MTM-PM1 module. This is a programmable power supply, the USB stem, which would do the digital I/O testing, and then the DAC2, which would do the voltage measurements. And then we would also have this connected to a USB hub so we could actually verify that key presses could be detected by the test system. And then kind of just a couple of test guidelines. If try and place your test points at least 1.9 millimeters apart. This is 75 thousandths of an inch, so fairly standardized measurement. It's like we can use test probes that can go down to 50 mil spacing. However, the smaller the spacing, the more delicate the probe is and the more often they will break. So if you can use 75 mil or 100 mil spacing, we definitely recommend doing that. Place all your test points on a single side of the PCB. Again, you can do double-sided probing, but it just adds complexity and kind of risk to the test fixture. If you're only probing one side of the fixture, it's really easy to make it and design it. Whereas if you're coming from both sides, it just adds a whole bunch more complexity. Place your test points a millimeter away from any other component. So this is a millimeter from the edge of the test pad. And this just makes it so that like if you're using a kind of spear tip probe or something like that, it's not likely to deflect and like hit the side of a resistor or something like that, which could cause false failures. And then make sure your test point pads are greater than 0.8 millimeters in diameter. And again, these are guidelines, like these are not absolute minimums, but if you're going into a new PCB design, these are a great kind of way to go about it, at least with your initial revision. And then if you need to go smaller, you can.
Yeah, you never want to be at the edge of manufacturability.
Yeah, exactly. Yeah. And there's times and places where, you know, it's what you have to do, but the vast majority of designs don't actually need to use more stringent requirements.
Yeah.
And yeah, that's all I got for today.
Hey, that's pretty great, guys. But while we've been going through, we did accumulate just one or two questions that you might be able to answer, might not, or maybe it's something on the roadmap further down the road. One user wanted to know, is it possible to incorporate this into some sort of an automated test, right? Do you need a person sitting there taking the boards, putting them in the fixture, clamping it down, running the test? Or, you know, can we hook up some SCARA arm or something?
With these InGaN test fixture bases, you can integrate automated opening mechanisms. However, they do not have an automated closing mechanism yet. So you can add a robotic arm that will close the fixture as well as load and unload devices under test. Definitely adds cost and complexity to the system. Another way to go about this is you can actually integrate the fixture in line. And in this case, it'll actually be part of the PCBA assembly line process. And so after a board goes through AOI and maybe, so AOI, automated optical inspection, it'll then continue down the line and go into an automated X-ray inspection machine if that's being used. And then after that, it can actually go into an online automated functional test system. And so in that case, a conveyor is actually loading the dot into the test fixture.
Interesting. Okay. Are there ever any needs for, and I don't know if I fully understand this question, but it sounds like a situation where you put the board down and then the pins come up from the bottom with pneumatics or whatever. I don't know that I fully understand that user's question. Do you know what they're talking about?
Yeah, so there's another like a way of designing these test fixtures where it's like the plate with the pins mounted to it is actually the plate that moves. InGaN does not use that approach. They use an approach where the top plate comes down like and then once it's kind of parallel to the board that's being tested, it comes like pushes down against it 15 millimeters. So it uses a different mechanical mechanism than the fixtures where the pogo pins come up from the bottom. One other thing that might be what they're asking is like there's what they call double stage probing. And so this is typically used when you try and integrate in-circuit testing as well as a functional testing within the same fixture base. And so with this, you'll actually have two different heights that the device will be set at. And the idea is you can use probes with different lengths. And so when it's all the way down in the fixture, every single probe will make contact. And so that's where you'll do your like in-circuit testing. And then for functional testing, you only need, you know, half of that many probes. And so you'll have it raise up and only the longer probes will make contact.
Oh, it's interesting. I never thought of that. And then our last question is, what about high voltages or line voltage testing? Do you guys deal with that at all?
There's just more safety concerns that you need to take into account, like when you get to voltages. It depends on safety, like with where it's being manufactured for exactly what you need. But we do have features that we can integrate into the fixture bases to allow for high voltages. We've done a couple of fixtures with high pot testing where we're like high pot testing modules inside of these things. In that case, there's safety interlocks to make sure that the fixture can't be opened when high voltages are present inside. For line voltages, it's pretty simple as well. You just want to interlock to make sure that if you open up the fixture base, you cut any line voltage access inside of it.
Makes sense. So tell me, and maybe we can hear a little more from Joe. What's the future of FixturFab? What are you guys going to be doing this next year, these next 5 years?
Yeah, so you saw a live demo of our design platform, and a lot of this knowledge that we kind of went over, we're just trying to build that into our software that makes it a lot easier to complete the design for these turnkey test systems. You'll see on our blog, we have a lot of these articles written about like how do you define a test specification? How do you select like what kind of instrumentation goes into a fixture? What are some of like the mechanical concerns that go into like the actual design of these plates? And we want to like build that into like the usability of our software. So you don't need to know this, but might be prompted to understand like, oh, I might want a cup tipped probe to access this kind of net instead of a spear needle tipped one. So a lot of it is just like working that educational content into our software and then making it a little bit usable so we can flip that switch from our customers, from us designing the test fixtures to our customers designing the test fixtures.
Well, I've got to tell you, I'm just blown away. This is a ton of work for two guys. And I know you're starting to add some, I think it was was it an application engineer?
We are hiring our second application engineer as of last Friday. So if you know of anyone, we're definitely interested in talking to them.
I haven't heard from him in a while, but I know one engineer that is just incredible. He's a workhorse. I don't know what he's up to lately. I'll have to reach out.
Mhm.
So
Yeah, this specific role would be at a workshop in Seattle, but in the future, we plan to keep on like building out that hybrid kind of structure of a company too.
In that case, no, I don't. I think he's in Ohio. I should have asked that. So, all right. Well, is there anything else you'd think the viewers of this particular webinar should know?
Um, yeah, like we love talking with people about test systems, and if you have any like questions or like just want more information on how to approach something, or if you have any suggestions for us or ideas, like just definitely feel free to reach out to us.
Yeah, I'd say take a look at our blog. And if there's something that we're not covering that you would like to understand related to any of the mechanical, electrical, or software work, reach out to us and like maybe we just didn't communicate that well enough, or we'll add a new article based off of that. And we'd also be very interested in like what kind of features you would like to see and like that revolves around basically hardware testing in general.
Sounds good, guys. Well, hey, I really appreciate the time. It's always a pleasure, and you are welcome back anytime that you guys want to tell us what else is going on with FixturFab. And I also really appreciate the fact that you used a teachmepcb.com design to demo this, right? That's the cherry on top of the sundae. That was adorable. I loved it. That was just great, man. I don't even know what to say other than I'm just going on and on now, and I'll continue to do this for like 5 minutes straight. I mean, seriously, I won't stop. I'll just keep. No, I'm kidding. It was really great. So, all right then. Well, Duncan Louder, Joe Selvik of FixturFab, thank you so very much. Viewers, thank you so very much. This webinar was brought to you by Royal Circuits. And if you have any PCB design needs, check out royalcircuits.com. We'll do right by you. So thanks. Bye.